So today our topic is regression analysis. We'll start with a very basic regression analysis, and then we will try to see what newer types of technology, newer types of regressions are available. Basically, regression analysis is when we are trying to study the relationship between the independent variable and the dependent variable. All of them are in metric, all of them are continuous. We can say that they are metric data, continuous data. Now, in case of regression analysis, just make it one point that there can be many independent variables like x1, x2, x3. Please remember this because we are going to use this concept later on also. X1, x2, x3, or it can be, we can have more independent variables, and there is only one dependent variable, and that is also in metric. Please write down on one page. X1, x2, x3, they are metric, and y is also metric. The example of the metric data is weight, blood pressure, age. They are all metric data, right? Now here we want to study the relationship that with the increase in the population, what is the rise in the demand of the TV sets. So it's basically a cause and effect type of relationship which we want to study, where we specify y as a dependent variable, x as an independent variable. This equation I'll explain later on, but at present just understand that y is equal to intercept, the constant term, plus beta 1 x. That is a coefficient of the independent variable plus error term. I will explain this later on, but at present just see this equation, nothing more than that. Now see this. Nature has not given any equation for any phenomena. We don't have any equation for the phenomena. For example, we don't have the equation for the global warming. We don't have the equation for rainfall. But the humans are trying to give the equation to this phenomena to reduce the uncertainty in this phenomena. So we can measure a blood pressure with the help of sphygmomanometer, which is the actual blood pressure. And say, for example, we have collected some samples, somewhere around 1000 samples, and on that basis we have developed one model. Now see, nature has not given any equation to us. Humans are trying to give equation to this phenomena to reduce the uncertainty. We want to find out that what are the factors which may affect the blood pressure, and by running the regression on some samples, it's just a hypothetical equation. No such equation exists, just a hypothetical equation is there, that the blood pressure is equal to 120 plus 1.1 times of age plus 0.3 times of weight. So this is a predicted blood pressure. The difference between actual and predicted blood pressure, do you think, all of you, just a simple question, that uh, we have taken utmost care of framing the equation, can I predict the blood pressure with 100% accuracy of any patient? Yes or no? Now, the answer to this is that it is not possible to accommodate all the variables which may affecting the blood pressure. Second, even if it is even if the variables are known, sometimes the quantification of such variables is not easy. So we can never get the 100% accuracy, and there will always be an error. There will be always a devil in your equation. But as far as possible, our you can say our efforts are in this direction to minimize this devil. Now, how we are minimizing this devil? On that basis only, the roots of Lasso and Ridge regression are there. Our sole objective in using the advanced regression is to minimize this devil. Is it clear? Please write down in the chat box what is our sole objectives. What is the sole objective of this using the advanced regression? To minimize the error. Fine. Let's proceed further. Now see these purple spots, which are the actual observation, and we are passing this line, blue line, right? Blue line. What is the full form of blue line? Is anybody aware about this? The full form of blue line is based, linear, unbiased estimator. There can be many lines which I can pass, but I want to pass this blue line in such a way that this, the summation of square of these errors, see the cursor, 1, 2, 3, 4, 5, and 6. The summation of the square of the errors of this is minimized, and that's the reason we say it is an ordinary least square. Is it clear? So purple eye is the actual observation by the spigomanometer, and this is a theoretical model which we are making. That is this one. Blood pressure is equal to 120 plus 1.1 times of age plus 0.3 times of weight. Now, what is the implication of this is that with the increase in the weight by 1 kg, the blood pressure unit increases by zero point 0.3, and with the increase in age by 1 year, possibly my blood pressure unit will be increased by 1.1 age. Now comes this part, which is a constant. Irrespective of your age or weight, even if the newborn baby is there, the newborn baby will have some blood pressure which is not, you can say, which is not dependent on any other factors. So when we are having a blood pressure which is some constant is there, and that's the reason we are introducing the constant. Now let us go back and try to understand this equation. Y is equal to the constant plus the slope beta 1. X is your age, and this is a error term, right? This can never be zero. At the most, we can minimize it. Let's see how we can run this regression equation in STATCRAFT. Really amazing software in the sense that it generates the R code automatically. These days, you must be listening a lot about Chat GPT. Now, let me show you how it's working. This is the interface of STATCRAFT. You can bring your new data from here, click on these three lines, click here, import the data. Now I'll write on here demo 1, upload the table. Okay, so I will bring the data. Just a minute. Employee data, click open, and you can see it has imported the data. Now, whenever there is a red line, it indicates that there is something conflicting. This variable is conflicting with the system variable. No need to worry. Just add some number to it, and the conflict will be resolved. Click OK, and the data is imported in the StatCraft. Now, this data is basically an employee data set, US 1994 data set, which is very easily available on Google. Right. Now here we are having salary, the current salary of an employee, the beginning salary of an employee, the job type. That is, with how many months the employee is with our company, the previous experience of the employee, the education, the job category, 1, 2, 3. That is, the employee is in clerical if it is 1, 2, custodial, 3, managerial, gender, male, female, and birth date. Now I want to make a equation that my current salary is because of which reasons, or my what are the factors which are contributing my current salary, right? So definitely I will consider education, because with the increase in education, my hypothesis is that my salary should increase. My beginning salary and its effect on the current salary, my job time and its effect on the current salary, my previous experience and its effect on current salary, right? Now I'll click here, regression, linear regression, dependent variable. I am targeting my current salary, independent variable. Now see, it's artificial intelligence. Okay, all of you, please see the artificial intelligence. Now see, in independent variable we require metric data, right? But as soon as you import the data in StatCraft, here it requires metric. gender is not metric. It will not get active only. It will give you it will give you a warning that you are trying to import the non-metric data in independent variable. So this is its power. Okay, let us activate education, then salary begin, job time, and previous experience, right? And I want to see the effect of all this independent variable on dependent variable. Click OK. Now see, first thing which is a niche of this software is it has generated the R code. See, I can just copy this code from here, right? And I can paste the codes directly in R. Control V. This is the first advantage, right? Then if I want to import or sorry, if I want to export this, I'll click on copy, Control V. Now let us understand the output. So our codes are there, the output is there. We will take the decision on the basis of ANOVA and the t-test, right? What is the null hypothesis of ANOVA? Null hypothesis of ANOVA is all the coefficients jointly does not influence the dependent variable. Okay, all the coefficients jointly. Remember the word in ANOVA, we are testing jointly. This is for ANOVA, right? This null can be written in different way also, or null is model does not exist. Model does not exist. Okay? Now, the desirable thing here is that the p-value should be less than 0.05. So, as the p-value is less than 0.05, we reject null hypothesis, which means that model exists. This is desirable. The p-value should be less than 0.05. Okay, please pay attention, all of you. Is the p-value less than 0.05? Just check, all of you. Is p-value less than 0.05? So you will say it's 7.69 and it is not less than. Okay. No, but it is e raised to minus 168. That is 10 raised to minus 168, which is very, very significant. So if it is anything which is e raised to minus 1 or minus 2, definitely it means that it is 0.00007, right? So 168 zeros are there. So it is highly significant. Now let us talk about the t-test, this one, individual. The null hypothesis in this case is all the coefficients individually, right? Now we talk about individually. Does not influence the dependent variable. And the desirable thing is here also we require that the p-value should be less than 0.05. Check. Is p-value less than 0.05 for uh, each variable? Please check and write down in the chat box, yes or no. Is it less than 0.05? Is it less than 0.05? Please check and write down in the chat box. Right. This means that these variables are significant and they are contributing in affecting the dependent variable, right? Now, what is the difference in ANOVA and t-test? Let us try to understand. In olden days, there used to be a promissory note, right? People used to borrow the money from the bank, and the promissory note was written as, we promise to pay a sum of so and so on so and so date, right? Now, when the bank goes for the recovery to this, those who have taken the loan, They will give the excuse that now their partnership has dissolved, and as partnership has dissolved, the promise which was given in the capacity of V is no longer valid. So from that day, the bank introduced one more term, and that is I slash V. That is I, that is in individual capacity we promise, and in joint capacity also we promise. This is exactly the same thing which we are doing, that individually also I am affecting the dependent variable, and collectively also we are affecting the dependent variable. So this is basically for system, and this is the individual capacity which we are checking. And the desirable thing is in both the case that the p value should be less than 0.05. Next thing which you should check is the p value. Basically, it's your report card of your model, report card of your child. Convert this into the percentage. It is 81 percentage. It means that all these variables collectively are able to explain 81% variation in the dependent variable. That is, 81% times we will be correct in predicting our the dependent variable, right? 19% unexplained variance is there. This 19% unexplained variance can be made because of many reasons. Let us see the reason one by one. The first reason is that all the variables are not considered, right? All the variables are not considered. Second, the functional form of regression is not appropriate. Maybe the phenomena is quadratic and we are trying to study it by linear. The another reason can be that we have not included the interaction effects. So there can be some reasons because of which we are not getting high R square. Now, many researchers try to introduce more variables, right? More variables in the equation, and they try to increase the R square. The second part of the story starts from here only, that by adding more and more variables, R square increases, but it gives rise to one more problem, and that is bias. Is it clear? What is bias? I will explain. But it gives rise to bias. Now, let us frame a very simple equation to this. What is the equation which I have got from this? So, I'll frame the equation and you'll have to remember this equation because this equation will get modified in Lasso and Ridge. Okay. So, let us write down the equation here. Control V. So, my current salary is equal to constant minus 16149 plus 669. See this 669 into education plus 1.768 into salary begin plus 161 job time minus 17.303 previous experience, right? Now, what is the interpretation? With increase in education by one standard, your current salary increases by 669 rupees. With increase in salary begin by $1, your current salary increases by $1.768. I will have to use the word dollars because this is the US data. With every increase in job time by 1 month, your current salary increases by $161. With increase in previous experience by 1 month, your current salary drops by $17.303. Now, it's quite surprising that with previous experience, increase in previous experience, how can the current salary drop? But we have seen in some disciplines like inform and IT sector that with the experience that over gradually over the time period the packages starts decreasing. You can see the packages of sports players it is quite possible that with the age, their package starts decreasing. So here in this field, probably we don't know the field. Previous experience is working against the current salary, and therefore it is decreasing the current salary. Now the second part of the story starts, and that is bias. What the researchers will try to do, they will try to increase the R square by adding more and more variable. Okay, what will this give rise to? It will give either the problem of bias or variance. First, let us understand this dart game, then we will see the numbers, then we will see the remedial measures. The ideal situation is this one, that all the dart should hit the bullseye, low bias and low variance. If we talk about this one, second one, uh, you can say that all the dart are in the proximity to each other, but they are not hitting the bullseye, right? So variance is low. The variability among the data is less. Variance is low, but it is biased. That is, the bullseye is the actual data and the predicted data is far away. So the bias is high, actual and predicted. Now let us talk about this third one. Variance is high. That is, the scatteredness is very high, but bias is low. Bias is low in the sense that if you take the average of this, you are nearer to bullseye. So biasness is low, but variance is very high. So we don't want any three of this. We only want low bias and low variance. So the fourth one is high bias and high variance. This is not at all desirable, right? Now the same thing, let us try to understand with the numbers. Actual 100, predicted 99, right? The predicted model, the blood pressure model, current salary. Actual is 100, 99 is predicted, bias is 1. And the variance is that suppose we had repeated this analysis for 3 times, we got the answer 98, 97, 99. We are very nearer to each other. These numbers are very nearer to each other. So the difference between actual and predicted value is less, so bias is low. The scatteredness of predicted value is near to each other, and therefore variance is low, and therefore the first diagram, low bias, low variance. The second case, 180, actual and predicted data, bias is very high. But in this predicted, the when we repeat the analysis 3 times, we got the answer 81, 80, and 7. Variance is low, but bias is very high. So this is the second case. Third case, 195. So 100 minus 95 is 5. Bias is low. Variance, if the experiment was repeated, we got the predicted value 60, 80, and 110. So variance is very high. Third case. And bias also high and variance also high. Fourth case. Is it clear? I hope you understood this concept. Now we have to do the trade-off between bias and variance. If I increase the model complexity, that is by introducing the square, by introducing the variables, my bias will definitely decrease, but my variance will increase. And if I keep my model simple, my bias will be high and variance will be low. So when model is simple, bias is high and variance is low. Simple model gives rise to the problem of underfitting, and complex model will give rise to the problem of overfitting. So there are two new terms which have emerged, underfitting and overfitting. You can see this. When I'm passing a linear line from this, it is a underfitting. I keep the equation simple. When I'm using the parabola, it is the proper fitting. And when I try to fit the data, fit the line, the theoretical line in this way, it is overfitting. Basically, in overfitting, your line is hugging the data. Is it clear? Your line is completely, you can say, engulfing the data in overfitting. Please write down in the chat box, what is your meaning of overfitting? What did you understood by overfitting? In overfitting, see this. You are making a theoretical line which will completely engulf, or which will, you can say, hug the data. it will be very nearer to the data. The model will become very complex. Biasness will reduce, but it will give rise to a very high variance. Here, you are getting the data you are making a linear theoretical model. Biasness will be high. Okay. If you are having a biased model, you are having lots of assumptions, and if it is a variance, no assumptions are there. So biasness gives rise to the problem of underfitting, and variance gives the problem of overfitting. Let me discuss the Fukushima power plant disaster and what was the problem. Directly, let us try to go there. This is the actual data of the earthquake magnitude, and it has taken this magnitude data. This magnitude earthquake has taken how many times in the past year? So 4.5. So how many times? 5. That is, this is a probability. So on this basis, they predicted that the probability of the earthquake occurring 7.6 or 8 is very, very less. So they designed the Fukushima power plant on this basis, that the probability is very less and the safety factor was kept 9, right? That 9 is, you can say, it is next to impossible that we will get 9 Richter scale earthquake. And they created the overfitted line, and on the basis of overfitted line they made the assumption that it is not going to happen. But within 2 years of Fukushima power plant construction, the earthquake of 8.6 hit, and this is the problem when you overfit the data. The second problem, underfitting. If we go according to the body mass and speed, the speed capacity of running, then possibly, see, with the weight, all these creatures are able to run faster. But if we go with this curve, then the elephants should be running fastest, but that is not the case. So this is the problem of underfitting. Now, if you are having high bias and variance, it gives rise to the problem of multicollinearity. I had told you that you should remember one thing, and that was x1, x2, x3. Researchers go on adding the variables in it. X1, x2, x3, x4, and so many variables are added. And possibly this will give rise to the problem of multicollinearity, in the sense that two variables will be highly correlated to each other. And because of this, the multicollinearity problem will arise. Let me explain this multicollinearity in a very simple way. Very, very simple way. Now imagine that there is a group of there's a group of 5 friends, right? And these 2 friends are having a very strong bond, right? These two are having a very strong bond because they were together from the school days, right? Now, what will happen is that these two will drive the group dynamics, right? They will drive the group dynamics, and what will happen is that they will make all others uh, they will make all others insignificant, in the sense that the decision taken by this two will be significant. The same thing happens in multicollinearity. When two variables are highly correlated with each other, right, their power will increase so much that they will make all other variables insignificant. Now, in multicollinearity, you will get very high R square. Your R square will inflate. But when you see the individual contribution, that is t-test, they all will be insignificant. In t-test, they all will become insignificant in t-test. And this is the problem when you go on adding more and more variables in your equation. Now see, this all rates are variables, and we are having a complex model having problem of overfitting. Too many variables are there and can give rise to multicollinearity. Now, how to control it? So for this, we are inserting one restriction on both the sides, right? So we are imposing lambda is equal to 10, and we are shrinking the coefficients and we are penalizing them. So by penalizing this, this power, the red coefficient, its estimates have decreased. Basically, our intention is to reduce the biasness. Now the the center one, they have completely disappeared because they were insignificant, though they were in the model. So by imposing the penalty coefficient, values of some variables will reduce. Complex model will become simple model. Variables having less coefficient value will be diminished and multicollinearity will reduce. See now, your original equation is this one. Now 2.3x1, which was having a very minimal effect, is gone. 1.4x raised to 4 is gone, and we are having a very simple equation: y is equal to 90 plus 90x square plus 13x cube. Now, from complex model, we have shifted to the simple model. Moreover, the values of the coefficient have also shrunk. Now, actually, how it's working? We are imposing one green line. That is, we are raising the bars of this, right? That is a penalty which is being imposed on the previous regression, and we are estimating this E1, E2, E3, E4, E5 and E6. If I go on increasing this line, possibly I'll get this parabola. So this is a slope and sum of squared residual. So this is known as a Ridge expression, where I'm introducing the lambda into slope square lambda, that is this one. We are keeping the line at lambda, we are raising this bar, and because of this our sum of squares have decreased. So lambda is equal to 10. Okay, so possibly I may get different parabola when I am imposing a penalty of lambda is equal to 10. If I impose a penalty of lambda is equal to 10, I may get again different parabola, right? So this is basically what we are trying to do in Ridge regression. We are imposing a penalty of lambda on the slope to minimize the coefficient. We are imposing the penalty. If you want to see the mathematical equation of it, that how actually it's working, it's very simple. See, this was our original equation. Yi is the actual minus predicted plus C. C is the lambda and the coefficients of the variable. C is the penalty which we are imposing, the lambda term, right? How we can do this? Now let me tell you one more thing, that whatever softwares which are available at present, no, not a single software is having this penalty imposition. It is only in STATCRAFT that we can impose the penalty. Click here, regression, activate linear regression. Sorry. Uh, Regression, Lasso, and Ridge. What is the difference between Lasso and Ridge? I will explain. So again, include salary and salary begin, job time, previous experience, and education. Click OK. Right now, what is the ideal value of lambda? The See, with the increase in the value of lambda, so this is log lambda, and 4443, where if I go on increasing the lambda, what will happen is it will go on shrinking the coefficients. So 4, these are the 4 independent variables. When I increase the value of this, again it will shrink, that is some variables will disappear. 3, 2, 2, 2, 1. Now let me show you one graph. Okay, just a minute. See, when I go on increasing the log lambda, basically these blue lines, they are all coefficients. Their values are shrinking. So you are compressing this coefficient to in such a way that when log lambda becomes infinite, all of them will become 0, because you have compressed the coefficient so much that they become 0. Now the question arises that what is the optimum compressions which can be done? So for this, in STATCRAFT, where this dotted line, right, cuts this trajectory, it is 7.8. So 7.8 is the optimal lambda which can be imposed, and you can get the better coefficients. Now let us see the difference in the coefficients which are generated previously by the regression analysis and with the help of Lasso. So I'll compare this one. I'll write down, yeah. Okay, all of you can see the difference, how much it has shrunk all the variables. Can you see the difference, all of you? So the overestimate which was there, right, the biasness which was there has been removed. See this. Can you see the difference? Education was 669. Now it is 336 because the penalty has been imposed. Salary began 1.76. Job time from 161, it's shrunk to 19.17, and previous experience minus 17. Here it is minus 20.66. Right? It is the number has increased. Now there are two regressions. One is Lasso and another is Ridge. The only difference between these two is in the mathematical term. Just a minute. In the mathematical term. In one case, that is in Ridge, we are imposing the square lambda beta square. So that is Ridge. And if I talk about Lasso, it is lambda absolute of beta. That is the only difference in penalty. This is I1 and I2 penalty. There is one more regression which has emerged, and that is the elastic net, which is a combination of Ridge and Lasso, right? Which is lambda 2 beta square plus lambda 1 beta 1. So at present we are working on uh, Lasso. To work on Ridge, again we will go back here, regression, Ridge, and I'll transfer salary here. Salary begin, job time, previous experience, and education. It will also give me the same output with lambda, the optimal lambda, and the coefficients. Now you are having three model, 1, 2, and 3. Which model is better? That you will determine on the basis of R square and the coefficients. See, this coefficients. Sometimes too much compression may give you misleading results. So you have to rely more on practical orientation also, that how much compression or rather how much penalty is to be imposed, right? So you will have to compare the model summary R square of all the three, and on that basis you will have to uh, use the equation. Now it is quite likely possible Lasso and Ridge, they both are penalty imposition only. They both are penalty imposition techniques. See, Ridge and Lasso both are penalty imposition technique. And by using this, we are able to get the estimates which are less biased. So you can use Lasso or Ridge from here, Lasso and Ridge. Right. Now it is quite likely possible sometimes that there are so many variables in your model and you are not aware that which can be significant and which cannot be, which is to be taken in the model and which is not to be taken in the model. So for this we require some automatic systems to filter the model. So we will go in linear regression, right? And a very small tick we will activate from here. Okay, let us include one more variable, minority here, and we will go in options, activate stepwise, and activate both. See, it is having an option of forward regression and backward regression, but my advice is both, run both. Now what it will do is all those insignificant variables, it will run the iteration on both the sides, forward also and backward also, and it will give you the best variables which can be considered in your model, right? Click OK. So minority is insignificant, but we have still included in our model. So it will start its iteration with the Akaike information criterion 8459. Basically, we are selecting the model on the basis of Akaike information criterion, and the criteria is lower the better, right? So here minority is there in the model, which is an insignificant variable. So what it will do, it will run the second iteration and it will throw the minority out of the equation. See, minority is not there in the second step, and therefore it will generate the best regression on the basis of second step. See this, it has run this thing, it has done automatically. Now imagine that if you are having 10 or 9 or 10 variables and you want how many times you will iterate it. So the answer for this is stepwise regression. Now comes the third part, and that is what to do when your target variable, see, the dependent variable which is there in regression analysis is metric. Okay, now there can be a possibility that your dependent variable is binomial, right? So in this case we are going for logistic regression. Binomial in the sense that who are the purchasers and non-purchasers of our product, right? Who are users, non-users of our product, yes and no, male, female. So here dependent variable is binomial, not metric. So we are using logistic regression, the non-parametric method. And if you want to use the parametric, it is discriminant analysis. Both these are available. The third scenario, your dependent variable is having more than two options. The ranking is there, that which one is better, 1, 2 and 3. In such scenario we go for multinomial regression, right? We go for multinomial regression analysis. Now how to do this analysis? Say for example we are having three candidates in our election: George Bush, Parrot, and Clinton. I'm just giving you an example, okay? Because the data has also been taken in that way only. Clinton. Now we have to make one category as a reference category, and all others will be compared on the basis of this reference category. Basically, all those who are aware about the concept of dummy variable trap, it is because of this reason one will become the reference category. This reference category will be there in dependent variable also, and it will be there in independent variable also. Okay, first of all let us see the data. We are having age into category, education, degree. Education has been, the continuous variable has been converted into the categorical variable, gender 1 and 2, and this is the president election of 1990 of 92. 1 2 3, I have removed the names from here. We are having three categories, 1 2 and 3. This is your target variable, right? And I want to see that what is the priority of the age category in voting the president. So age category and degree, they will become the independent variable, and gender. So you will go in regression analysis, and from here you will activate multinomial logistic regression. Dependent variable will be the president 92, And the independent variable we will consider is age category, degree, gender, right? In options, activate the confusion matrix, the variable importance, and analysis of deviance. Pseudo R square, likelihood ratio test, click OK. Codes are ready. This we will interpret later on. This also we will interpret the later on. First thing which you have to say is analysis of deviance. Right? See the p-value. It is necessary that this p-value should be less than 0.05. Is it less than 0.05 in analysis of deviance? It means that these categories are able to explain the priorities. Now we will see the variable importance. The overall age category 4 is having a better explanatory power in comparison to all other categories. Degree 2, the degree 2, that is a category 2, is having a good explanatory power, right? Now see, there are 4 age categories. One will be reduced, 1, 2, 3, 4, and gender also one will be reduced. Okay. Now I have copied this result, this coefficients, and the p-value on the word file for interpretation. So let me directly go there only. How to write the interpretation of this. The same file. See, it is the same file. No change. It's the same thing which I have copied from here. You have to see the p-value. Wherever the p-values are less than 0.05, the same you have to highlight in coefficients also. Wherever the p-values, see this in STATCRAFT, you have to see first the p-values, this. Okay. So wherever the p-values are less than 0.05, those categories are significant in deciding the priorities. Now, if I talk about the second one, 1, 2, 3 are there. First became the reference category. 3 president. First became the reference category. 2 and 3. We are trying to write the interpretation on the basis of 2 and 3. So here, as the p-value is less than 0.05, this means that age category 3 is significant. Now, how will I write the interpretation? As a p-value of age category 3 is less than 0.05, so voters prefer candidate 2 minus 0.538 times of candidate 1. 1 is our reference category. Okay, let us take one more example, and that is this one. Its p-value is less than 0.05. As a p-value of age category 4, let me make this 4, is less than 0.05. So voters prefer candidate 2 1.66 times of candidate 1. Okay. Now let us write the interpretation for the degree. As the p-value of degree, that's the college degree. As the p-value of the degree 1 is less than 0.01, this one. So voters prefer candidate 3 minus 0.59 times of candidate 1. Okay. Now I give one task to you. Can anybody write the interpretation of gender? This one. As the p-value, okay, of gender 2 is less than 0.05, so voters prefer candidate 2 minus 293 times of candidate 1. And here 0.463, candidate 3 is preferred 0.463 times of candidate 1. Now in case of in case of multinomial logistic regression, we cannot have the R square because the functional form has changed, and therefore we are having the pseudo R square. Pseudo R square. And here also the interpretation is same, that it should be nearer to 1. This is a pseudo R square. This one. It should be nearer to 1. But its explanatory power is less. The second thing which you have to check is the confusion matrix. Basically, how accurately the prediction works. This is the actual data and this is the predicted data. So the actual data, in actual data, those who have voted for 1, and in predicted data also those who have voted for 1. So it means that 198 is correct. But this is a false thing. The actual data is 2 and the prediction is 1. So this is the false classification. Okay. Let me explain this with a simple example. So we all have recently passed through the pandemic and we were all using the COVID kit. Okay. So a person is having a COVID, a person is not having the COVID. So this is patient. Okay. And here I'm inserting the kit. Yes and no. Okay. So what is a success for me? A patient is having a COVID and the kit also predicted it that he is having a COVID. Is it a success? Say yes or no. Is it successful? Is the kit successful? The patient is not having the COVID and the kit also detected it that the patient is not having the COVID. Is it successful? Now the failure is the patient was not having the COVID, but the kit predicted it. This is failure. And this is also failure. So in multinomial and binomial logistic regression, we are looking for more and more the success, diagonal success. And this STATCRAFT will generate the success. And that success is measured with the help of accuracy. Accuracy is 0.49, right? The accuracy in prediction is 0.49. It means that it is less than 50%. It's bad. Why it's bad? Because your model is able to predict the thing which is less than even the nature's probability. Nature's probability is 50%. And your accuracy has gone down below 0.49, 0.5. And therefore, it is not good. So they have came out with the concept of hit ratio. And that hit ratio is that you should at least get an accuracy of normal probability. It is a normal probability of 2 class plus 1/4 of the normal probability. Okay. You should get the value above it. Say for example, you are having the target variable as purchasers and non-purchasers. So what is the normal probability? 50%. So your hit ratio will be 50% plus 1 by 4 of 50%. It will be 62.5 percentage. It should be more than 62.5 percentage. So if your model crosses above this, you can say that the model is successful. Now if you are having three categories, president, pre-president, priority 1, 2, 3, the normal probability is 33% plus 1 by 4 of 33%. Your hit ratio should be above this, then your model is successful. In last, uh, in last, let me try to explain the principle of Occam's razor. If you hear a sound from the top floor, from the floor above you, and nobody is staying there, what can be your theories? Tell me, what can be the theories which you put forward for the sound which is generated? Okay, what can be the theories which you will put? The first one is wind, the wind turbulence. Second, it can be some rodents, can be some pets, right? It can be a ghost, and it can be the alien. Okay, alien. You started with the simple theory and you went to the complex theory. All the machine learning problems work on this principle only. Make your model as far as possible simple. Don't try to complicate, don't try to make the complex model, right? Because the explanation of the complex model is very difficult to give, and that's the reason each and every statistics which is being generated, they are converging to make the model simple. And the objective of Lasso and Reach is to make the simple model. So thanks to STATCRAFT that they have thought about this and they have came out with this algorithm to make the model simple. Is it clear? This is all about Lasso, Ridge, Multinomial in STATCRAFT.